Alright, it'll come as no big surprise that we will run this proof down by cases. So, in the first case, suppose that the domain of f is w1, the range is w2. Obviously, we now have a one-to-one order-preserving function from w1 to w2, one-to-one and onto, so that's an isomorphism. Case 1 holds. Of course, we need to show that exactly one of the three cases holds, and so we've shown that one of them does. We would also have to show that neither of the others hold, but that's very easy from this point, so you just got to use some of the theorem or lemmas and corollaries that are proved earlier on. In any case, we can move on to the next. So suppose that y1 is less than y2, and y2 is an element of the range of f. We can argue that y1 must also be an element of the range, and we could do that by using the fact that y2, being in the range, there must be some pair, call it x2, y2 if you want, but that these two initial segments are isomorphic. Since y1 is less than that, we get an initial segment of w2 determined by y1. We can use f to backtrack the initial segment in w1 that corresponds to it. They'll be isomorphic, and therefore y1 is in the range. Okay, but the proof is not hard. I mostly just kind of breeze through it because you should be able to reproduce it for yourself if you want to. In any case, moving on. Let's then assume that the range of f is not equal to w2, and we will then argue that the domain, right, whatever the domain of f is, the domain of f must be equal to w1, and we'll sort of take it from there. But if the range of f is not equal to w2, then we can take the difference between w2 and the range, and that's a subset of w2 must have a minimum element, call it y0. It would be pretty easy to show that the range of our function is equal to just the initial segment given by y0. So for contradiction, suppose that the domain of f is not equal to w1. In that case, then, we could again take the set difference, find the minimum element. It will, we could call it x0. We know it must exist. At that point, we could argue that the initial segments given by x0 and y0 must be isomorphic. And if they are isomorphic, that just tells us that w1 is in the domain of f. But, after all, we took, that means x0 is in the domain of f, but we took x0 to be the minimum of w1 minus domain f. That means it can't be in f. So you have a contradiction. Okay. This establishes from here, we assumed it for contradiction. We have our contradiction. We now know that the domain of f is, equal to w1. And now we have that w1 is isomorphic to an initial segment of w2, and that is showing us case 2. The proofs of parts 1 and 3 are not hard to show at this point as well. Case 3, assuming that the domain of f is not equal to w1 and proving that the range of f is equal to w2 goes very much in the same way. So we end the proof here.